biggest takeout for a lot of the people that have been a part of this presentation in the past. And then lastly, we'll finish on questions and answers. All right, so Gamcorp, if you haven't worked with us and this is your first time experiencing us, a bit of a background on what we do. So we work on large commercial solar projects. We've been, very, very blessed to be a part of some of the biggest projects in Australia, and we've really, gained a lot of experience based on going through some of these larger installations, and obviously all the way down to as small as residential style buildings, doing assessments on them. We do service other industries like steel fabrications, playgrounds, and bridge designs. But I would say that the majority of our organization revolves around the commercial solar industry. And as of recent times, over the last maybe year or two now, we've been also doing physical on-site testing for roof sheet clamps, which we'll go into a bit more detail later on as well. So the assessment process, when we do an assessment, it's not necessarily, we're not just looking at the structure itself. I would like to, this is, don't take this to exact percentage here. It's not to exact percentage, but I would say 50% of the process is actually analyzing the structure itself, and with the capacity of the purlins and the rafters and their limits in deflection. But there is also a huge consideration for the fixing assessment, which is effectively that the small connection between your panel array frame and the roof sheet itself. And that ranges depending if it's a screw or if it's a clip lock high strength or builders, and the capacities differ. And lastly, making sure that the array frame is suitable for that height and that region and everything like that. We do a small check in regards to that. And there's obviously more detailed checks if it goes out of the general certificate's kind of boundaries. But in general, that's how the assessment's broken up. So sometimes it works, the structure is fine, but the fixing is not good. And other times the fixing is great, but the structure itself is not strong enough. Now, moving on, we'll go into why we do what we do. So we've had cases in Australia, and we're not going to go into too much details about that, but a big case that's happened overseas is the Kendall School case in 2018, where we saw that the installation method and the structural integrity of the fixing between that roof sheet and the panels actually caused a massive destruction in the school, and it actually injured a few students as well. This was considered to be a safety spot for when of extreme wind situations, and it itself was affected quite heavily. The warning signs structurally that we like to say is there's many different regions, but the reason I brought this up is that I understand that geographical location makes a big difference, being in the northern parts of Australia and the wind regions in that area, and also the structural factors where your things are spanning too long and there's no bridging or lateral support to your structure as well. And a lot of the times new buildings, we'll go through that, why new buildings can be a bit of a scare for us as well, but we'll go through that a bit more in details in the project considerations. Let's move on to the most basic that we all know about, vertical loads, which is the dead loads of the panels, which is its physical weight. The array frame and the panels can be considered quite a lightweight structure, and for that reason, a lot of people think it's fine. And the truth is, when initially you're designing for a building as an engineer, when you're looking at the loads, the potential loads on top of a building, there is a lot of considerations around a certain amount of weight and a certain amount of load. But we found that a lot of the times that if it's a very old building, or if it might be on its limit, and by adding this additional weight, although it's considered quite small, can be a problem. If I'm being honest, it's not predominantly the problem. The predominant problem is the next slide, which is the horizontal loads, which is the wind loads. A lot of people, we get a lot of calls, and a lot of, especially when they first engage in Gamcorp, thinking that it's just a load issue. It's not. Wind is being the most critical consideration in our assessment, both in the deflection of the structure and also in the fixing between the panels and the roof structure itself. Common statements is about the fact that wind forces can't be the critical factor, and it definitely is in many cases. And the same, and understanding the difference between different areas of Australia. If you've designed something and installed something in Victoria, it'd obviously be very different to something that's been done in Queensland. And understand why the wind regions in that area are quite high. They're significant in regards to potential high gust wind speeds compared to the Victorian side. There's a little image here that shows a building. We'll go a bit more into details on why the corners are more affected than other sections, but understanding on this face, you have one face of directional wind here, another face of directional wind here, but in the corner, you have both faces of directional wind, and it's kind of a critical spot here. We'll go into that in the following slides. So the structural components. Now, the structure is made up of many different components. From the top, you have the roof sheet cladding, which protects the building for rain and other purposes like that as well. But then it goes down to the purlins, which are the direct support of the roof sheet. Underneath the purlins, you have the rafters, and they're the direct supports of the purlins. And the rafters then just take the loads from the purlins and the roof sheet down to the columns, and the columns take it down to the foundation. And the foundation is obviously, as most would know, is the most critical part of all of this. But if we're just looking at solar panels and how they affect the roof structure, then we don't really need to analyze the details around the foundation. The direct critical areas that are being affected are the purlins and the rafters and the connection with the roof sheet. So it's pretty much the three elements you see up here. Although you can argue that obviously load is transferred down, we make assumptions around the fact that the columns and the foundation are going to be less critical than these higher elements up here. Going back to what these elements look like, if you're looking at a bird's eye view and you have a ridge line along the center of your building, as you'd expect for most warehouse type structures, you have portal frame rafters spanning up and down the page, and you have purlins that are spanning left or right on the page. And effectively their spacings and spans can affect the strength of the structure. If you have quite a big purlin, which would be a C or a Z section, but they're spaced quite far apart, then it would be just as bad as having a very, very small purlin, or good, I should say, as having a very small purlin, but they're spaced closer together. So necessarily having big structures and big beams doesn't necessarily mean all the time that you have, the solar insertion would be fantastic and everything will work well. It really does depend on the amount of spacing and their spanning lengths as well, and also the conditions of the lapping and continuity of over the rafter. Go a bit more into that a bit later on, but just understanding the main elements that we analyze are the rafters, the purlins, and the roof sheet, the connection there as well. So one part of our assessment is understanding the wind calculations. An overview of the formulas are here, but the reason I share this slide is to understand that there's many factors, and each hold a certain weight in percentage. The wind speed may hold, of this formula might hold a 50% weight or a 30% weight. But then also the terrain category, the direction multiplier, the shielding multipliers, and the topographical multipliers, they also hold a certain weight to the building as well, to the assessment as well. And effectively, when you are doing an assessment, although it might be you might be shielded by the buildings and you might be enclosed by the spaces, the wind in that area might be the critical factor that puts your assessment into more of a negative situation. And again, the design wind pressures are determined by whether you're going flush or tilt, or the zonings of the building, and then the considerations are taken here. So if you have a pitch roof that's less than 10 degrees, you have a kind of standard corner zone, edge zones, intermediate zones, and so on and so forth. When you have a flat roof with no ridge line in the middle, which is the flat one directional slope, then you have a similar thing. But then when you have something that's greater than 10 degrees, you see that there is a bit more complexity in regards to the pitch roof and the zones at the ridge area. And also in this, there's no corner zones as such, but there is the corner zones are effectively wrapped around the whole building, and the intermediate zones, and so on and so forth. So the whole point of this is to understand that as the building shape differs, the zones will also differ. And these zones have been, as I mentioned before, calculated by directional wind. So if you've got a wind coming down here, sorry, the zones aren't, the size of the zones aren't calculated by the directional wind, but the forces, and why these have got more pressure than this internal area is because this section is getting a wind force coming on this directional face, this one also, and in this corner you're getting two directional wind pressure. And then on one edge you have the direct impact, and then it obviously reduces as it goes towards the center of the building. Won't go into too much more detail on that, but last thing I will mention is that these zones, the size of these zones, are actually determined by, according to the standards, determined by the size and dimensions of the building. Now, it is a pretty simple formula in a sense, but they're not our decision. It's definitely decided by the physical shape factors of the building itself. Going to the next page, roof sheet types. Now, if I was to ask you to take anything from this presentation, it would really be this slide, and I would also urge you to join the webinar next week on Friday in regards to the roof sheets. This is probably the biggest misconception or lack of understanding in the industry is about concealed roof sheets. Concealed roof sheets, when you have you might have an amazing structure, but if you have a concealed roof sheet on top that has very little capacity, When you put your clamp on that, that is going to be the weakest part of your system. And when it is your weakest part of your system, then it doesn't matter how good your structure is, your panels will dislodge at a high gust wind pressure according to the standards. Now, understanding how that works is we've got a product here, both created by Fielders, which is the same manufacturer. The sheet widths do differ slightly. One's 700 wide sheet, and this is a 630 wide sheet. But the capacity when we talk about the clip is actually the internal clip that the ridge is kind of covers. So when a roof plumber is installing this along the purlins, they'll add these clips and they'll screw these clips down to the purlin, whether it be timber or steel, and then they'll physically place the roof sheets on top of the clips and they lock into place. Now, in a case like this, you can see that the Fielders 700 King clip has a simple clip that's screwed down, comes up, and it has very small little hooks on the top side of the clip. But really, the real strength between these two metal elements is the friction between the roof sheet itself and the clip. Now, friction is not a great force, and when we do the testing on this, and when manufacturers have done testing on this particular roof sheet with a particular clamp, they've got capacities of pressures of about 0.8 kilonewtons, quite small in the scheme of it. But if you look at Fielders' exact other product, where you can see the same kind of thing, where they screw down their internal clips down to the structure, but in this case, the clips interlap onto the roof sheet. They're also locked down on different corners of the rib as well. So you can see that it's got significant more strength here, and the strength of this kind of goes up towards the high strength level, which is 2 kilonewtons plus, because they really want to make sure that this roof sheet is really tied into the building without penetrating it physically, without penetrating the roof sheet physically. Obviously, it's a lot more expensive as a process, not only installation but as a product. So we see less and less of the better roof sheet types, and we see a lot more of these cheaper roof sheet types. Common points: penetrate was no concern. The exact sheets needed to be identified. It's very true. If you're using screws, if it's a corrugated or a trim deck type of roof sheet, then the capacity is actually in the screw itself, and that screw is obviously penetrating into the timber or steel structure, and the depth of the penetration into the timber structure will give you a certain capacity, and the penetration through the thickness of a particular steel will give you a different capacity. So screw capacity does range, but in general, it's a lot higher than a little bit of friction between two metals, or even this interlapping metal sheet kind of style clip. So screw capacity, when you have screw capacities, we don't really need to know exactly what type of sheet it is, but just more becomes a critical factor of what it's being screwed into and the depth of that screw. Roof sheet clips are commonly the weakest part of the system, which is a very common understanding from us now, that when we see that we have concealed roof sheets, we know that fixing is probably going to be the most critical concern. Now, it could still be the structure, but it just it's a level of warning for us. And probably the worst bit about this whole point is that if it is unknown, we must assume the worst case that has been tested and that's been certified. So there's many types of 700 sheet widths. You have from your Lysat Classics, your Lysat High Strength, your Fielders, there's many different types. The problem with this is that if we go on a site and we see that it's a 700 wide sheet, and we see that it's got two straight lines, like the majority of them do, and there's 10 plus manufacturers, if we can't identify which manufacturer it is, according to our understanding of the code and everything, we have to assume that it could potentially be Fielders. Now, if it's in Queensland, Tasmania, we can argue it's not available there, but regardless, it's something that we know that's been tested for a 700 roof sheet, and we have to take them very low fixing capacity into consideration when doing the assessment. So any extra information you get about defining what a concealed roof sheet is would be a big help for you guys, just to get a bit more capacity in the fixing component of it. Now, the best way I can advise that is to actually lift up the roof sheet, temporarily lift it up towards the edge, and you can just take photos of clips, because even if we can just say it's not Fielders or it's not a particular low type of, it would increase your capacity up to the next range that has been tested. Let's move it on to panel sizes and tilt angles. Does play a big part in the assessment as well. I had the pleasure of joining One Shop Warehouse around the national tour, where they were talking about different panels and different things, and one that came up was the Jinko Tiger panel, where it's slightly smaller than your 2 meter by 1.1 meter panels, and it still gives a certain amount of a certain amount of output energy-wise that's quite advanced. The reason I bring this up is as technology gets better, we see smaller size panels, and obviously the smaller the panel, the less wind exertions on the panel itself, in the face of the panel. If it's a row of panels, then it doesn't really matter what size it is, because the row is still a lot bigger than any one panel. But in general, by reducing the size of your panels, it does play an effect. I won't say it plays a significant effect in that fixing assessment. It may only be 5 or 10%, but it does play a part in the actual structural assessment process and how wind is calculated. Now, another point, and probably the main point I want to raise with this slide, is that tilt angles are very critical. What we found is that when you initially design a building, I won't go too much into the mathematical detail of this, but when you initially design a building as an engineer, you allow for a certain amount of wind pressure. What we found is that wind pressure is actually quite equal to or similar to a panel when it's at 10 degrees. So when a panel is at 10 degrees or lower, I should say, the building has somewhat been, like, the certain considerations when designing the building has been considered for these type of wind loads. Now, as soon as that panel exceeds 10 degrees, then we can actually make a statement saying that building, although it can still be assessed and it could still be fine, it wasn't initially designed for that type of pressure, or that higher end limit of the pressure. And therefore, we actually need to do a more detailed assessment. It doesn't affect you in regards to costing or anything like that. It just takes a bit longer for us to assess the rafter and the purlin and make sure that it can withstand the greater loads than what it was initially designed for. And in many cases, it still is okay. I don't want to just say that if you want it over 10 degrees, it's not going to work. It definitely can still work, and we've seen many cases of it working. But there is an extra consideration for us. Once it gets past 10 degrees, we actually need structural drawings. We can't do it based on checklists and a few other things. But the reason behind that is for understanding when it's initially designed, it allows for a certain wind pressure. After that point, it doesn't allow for that wind pressure anymore, and we have to make sure that the whole structure is okay with it. And lastly, flush obviously minimizes. It still obviously adds a certain amount of wind pressure, but it minimizes the effect of that. But there's obviously other concerns with that, with self-cleaning and everything like that. Moving on to the next slide, let's look at some project considerations. So these projects that have come up from a bunch of commonly asked questions, and we'll go through some commonly asked questions as well. But in general, these project considerations have been quite helpful, and I've been putting these in since we've been getting great feedback and conversations from our clients directly. So the first one is building structure types. So when looking at a building like this, let's say hypothetically was built in the last couple of years, we can see that it's got a straight ridge line down the middle, and it's quite big, and it looks like it would be symmetrical in that sense. So you'd see whatever's on this side, you can assume it will be on this side. What we've found that when we actually analyze structural drawings on this, particularly with new buildings, but it has happened for older buildings as well, is that we get something like this. Now, this isn't the drawings for that building, but in general, you get situations where you find that one building is got a set of purlins in this middle area here, and then some outer purlins that differ, and then some outer purlins that differ again. The reason this happens is because the pressures that engineers are put on these days to design buildings more efficiently and with less steel and roof beams are charged effectively by weight. When you can, save, we know that as I explained before, the wind pressures change, right, from the edges to the center. So a builder will tell the engineer that he understands this, and he wants smaller purlins in this section and bigger purlins where it needs to be. But in the past, they would design the maximum wind pressure and put the purlins throughout the whole building. But now, as we're getting more advanced and we have more models and more systems, we can save, $100,000 in construction costs or $50,000 in steel costs by reducing these purlins in the center part, as it's facing a lot less wind pressure, which is all good and well. The only problem is that when we want to do an assessment on this, obviously the assessment of the capacity of these purlins when adding additional loads will be different to the capacity of these purlins when adding additional loads. These purlins will naturally be stronger, although faced with high wind forces. But in regards to dead weight, we're not talking about wind forces at all now. These purlins will act a lot better than these purlins will, and so on and so forth. So it becomes quite a tricky situation for us when your team members will see one building and they'll say, oh yeah, it should be one assessment, or it should be a very quick process. But then we find out there's 4 or 5 different types of purlins, and they're spanning at different lengths, and they're spaced at different things, and the thickness differs and whatever it is. So The point I'm trying to make by this slide is understand that new buildings adds a whole lot of complexity with our assessments. Now we can assume the most critical, do an assessment on that and apply it throughout, but that might be a negative for yourself because you could have had a, you know, quite a big area with a lot less rails, or you know, greater spaced fixings, which saves you on your clamps and everything as well. So understanding new builds aren't necessarily you know, the best option at all times. Another consideration is multi-site projects. Kind of going back to the point I made last time, we could go and do a big building like we saw in the previous slide. And although it's only 2 purlins, the assessment budget, let's say hypothetically, was, you know, 1,100 or so for that project, and we could put a megawatt on that. And because all we're doing is assessing the purlins and the rafters and their capacities, and then saying, according to these capacities, this is the allowable amount of solar panels you can put on there. And we're analyzing any one particular type of purlin and rafter. But we have a case like this where there's multiple types of buildings. The kilowatts are only, you know, 100 or 200 kilowatts, let's say, for this whole project. But the price for this may be, you know, closer to $10,000, you know, 10 times the cost. And it just comes down to the simple fact that when we're looking at something like this, we can make assumptions on what buildings may be similar, but we have to assess each set of purlins and rafters separately, right? So this building structure and its deflection limits will be very different to this building's structure and its deflection limits. This roof sheet may be, you know, quite a strong roof sheet, but this roof sheet here may be, you know, a very, you know, thin and you know, badly constructed roof sheet. And so there's many other points and factors we have to consider when we're doing a multi-site project. And I just want to make clear that even in the same zone, even in the same area, you might have huge different results between this building and this building, but it could be because of its structure, it could be because of its roof sheet type, it could be because one was screwed and one was fielders, or whatever it is. So, and the cost of that, obviously, for us, it takes us, you know, 10 times the amount of time to do this for a small 200 kilowatt project over a 1 megawatt project that would only be the assessment between one rafter and one purlin, or maybe one or two. Hope that is a bit of clarity for some people that I'm sure I've had many conversations with about. Another really common one that we find is, God bless you guys, you love your north faces, and we like to help you out, and we try to do our best to help you guys out to, you know, to maximize your energy output. But the truth is that when you over stress the building on one side, it creates other issues. So here we have a great example where someone came in and they wanted this kind of installation, which I'm not saying, again, it's not possible. In this case, it wasn't, but you're significantly adding a lot of load on one side of the building. Now, if you want to, this obviously isn't the exact shape that this is, but effectively in the building strength is in its portal frame. A portal frame is effectively a U-like, upside down U-like structure that connects down from the foundation. Column goes up, rafters go across, and column go up, and that's kind of a rigid system. It's effectively one piece that changes directions. When the portal frame is created, it's created in its strength is in its shape, so it's like a truss-like system. And when you are overloading the truss on any one direction, so in this case it's applying wind loads, but it could be a dead load force in this case, right, where we're putting a lot of panels on one side. What ends up happening is you put a massive amount of deflection that will look similar to this wave of deflection here on this side of the truss. What happens there is you get a bow on this side of the portal frame, and then here you get and like it trying to counteract that force, it extends out. Huge amount of deflection, and now the strength of that truss, the strength of the triangle is no longer there, or it may still be there, but it's definitely heavily affected. It's definitely not what it's been designed for. Right, it's designed for similar loads on either side, you know, uniformly distributed loads on both sides. It's not designed for heavily overweighted one side assessments. So it goes, the recommendations I can put, if you need to do this and you want to do this, it could be as simple as, if you're going to put panels on this side, put 2/3 there, but put 1/3 here, right? If you have to reverse tilt it or whatever it is you need to do that, and understand there's energy output requirements you guys need to meet as well. But understand that you're putting a lot of major stress on one side of this triangle, one side of this truss, and you're causing these deflections to happen. And what we've seen in many cases in the past is that you start seeing that, you know, the pipe work or you know, some things that are hanging off the roof starts to crack or sway or bend, or there's multiple range of issues that we've had to deal with in regards to overloading one particular side. Usually we get called in when it's a bit too late, but it means that they have to relocate panels or remove panels. But the truth is that when you're initially designing this, you have to make sure your sales team know and your PMs know that it's not good to heavily weigh one side of a building. Lastly is inspection requirements. So we have it's a great project like this, and quite a big space with a lot of panels on it going over the whole thing. When we initially got told about this project, we were told, all the buildings are the same structure. It's pretty straightforward. It shouldn't be too bad. And in my head, I'm like, great, if they're all the same structure, as I mentioned before, we'd do a predominant check on the most critical, and we could probably apply it throughout and do some other, minor checks and this and that. But the problem is that after actually going to the site, we found that although they are the exact same structure, they're all being used significantly differently. Right. In one section, you have a freezer that hangs off the roof. In another section, you have, heavy tilt panels or heavy ceiling panels or whatever it is that are hanging off the roof as well. In other sections, you've got something on top of the roof that's adding additional loads. And in some sections, you've got absolutely nothing, but the doors are always open and the wind flow is just significant throughout that whole area. So what we thought was going to be quite a quick and I would say reasonable, budgeted, quite efficiently, ended up being a massive project that had a huge amount of considerations, and because of the way the building was used. So the point of it and the reason for this slide is to understand that it's not necessarily just about the structure itself, but when the structure is initially designed, it's put a certain allowable loads on there. But if you go there and you see that there's a massive new fan or new ceilings or whatever it is that's adding additional loads onto that structure, then you can see that it's going to play a big part in how much further loads you can add on top from your roof sheets. So definitely look at how the building is being used and let your structural engineers know, look, although I want to install this amount of panels, I want you to know that there is, a couple of big fans that I haven't seen or that isn't normal. And you guys are all well aware of things that are somewhat standard. And again, to make this point as well, it might have initially been designed for. And there's been cases where we've had big warehouses with, walkable ceiling tiles. And although walkable ceiling tiles are quite heavy, the initial engineer design for walkable ceiling types, so the additional loads were still allowed. The additional loads of solar panels were still allowable because the purlins and everything had obviously been designed to accommodate for them walking ceiling tiles. So doesn't mean that it's, again, going to affect your installation, but it does mean it is something that you have to consider as a part of your considerations when using a roof, how the roof is actually being used. Guys, that was an overview. I'm just going to go through it again one more time. So understanding the vertical and horizontal loads and how they differ. Understand that, fixing assessment is probably the most critical of the fixing, which is the uplift calculations. And understanding how much the roof sheet types can play a part in it. If I could bold that sheet, I really would bold this slide here. That is probably the most critical part, and the biggest confusion around our industry right now is that roof sheet type. And again, I urge you to join us next Friday for a bit more detail of why roof sheets are the way they are and what we do to overcome them, what testings we do and stuff like that to make sure that we can still be safe when putting panels on top of a roof. And lastly, going to the project considerations, we talked about, one building, although it might be brand new, has multiple types of purlins and multiple types of structures in there that have to be assessed separately. And if they're not, and they're assessed from one most critical span, then it could add costs for your actual installation process. And then we went to multi-sites and dead load deflections. And that's probably the next one I would probably bold would be that dead load deflection slide that we talked about, that the portal frame has its strength in its shape and not necessarily by loading the northern side, you are creating a huge amount of deflection throughout the whole general integrity of the shape, which can cause further damages, dislodging or pipes breaking and so on and so forth. And lastly, when you're out on site and you're doing inspections, take note of what's being hung off the roofs, take note of what's actually happening on the building. Now, I've added a few general questions that are commonly asked me I present this to companies directly as well. And some of the questions that I've got back, I just want to relay them and kind of put them together. So I'll go through these, and then in this meantime, I'm going to ask Martin to just start collating the questions that you guys have asked here as well. So which structure is stronger between web truss and normal truss? It's a very common question. There's too many variables to make statements around whether web trusses or normal trusses are stronger, or it's dependent on their spans and their spacings. So web trusses usually span longer lengths because they are stronger as a system. But for your solar installation considerations, understand that you could have a major, a magnificent web truss underneath the roof sheet, but it's spanning really far apart. So it puts more pressures on your purlins, and then because it puts more pressure on your purlin, it puts more pressure on your insulation deflections that's going to be added because of insulations. So there's no right or wrong. You could have a really small purlin that's spaced really close together, which is like a residential timber roof, or you can have a quite a large purlin that's spanning quite large lengths. That could also be a bit of a problem. A lot of it questions around our pricing scheme and how we price. I would like to direct you guys to the Gamcorp website under solar engineering in the top right. You can look at our list of our services and how we price our assessments. Effectively, it's priced by, as I mentioned a few times today, the purlins and rafters we have to assess. As the combinations of purlins and rafters, their spans and their spacings differ, then we need to effectively, do a more detailed analysis and add more components to the assessment. But we price per roof structure, not by the size of your installation. Pallet loads is a big one. So how do pallet loads affect the roof structure throughout time installation? The common question for us, and we have to understand that pallet loads have not been designed for when a building's been designed for. I would say for the majority of cases, there are some concrete roofs and other types of structures that will allow for that much amount of load, but your general warehouse hasn't been allowed to have a 500 kilogram plus pallet on any one area. So it really is critical for you to understand that when you're dropping pallets on, obviously there's other ways to install with scissor lifts on the edge of buildings or whatever it is, but in general, if you're palleting pallets on top of a building, make sure that there has been huge considerations on what you're doing. We have an assessment called pallet assessment, which can help you with that. But alternatively, and just to mitigate the risk, and if you don't have the time or for whatever reason you don't want to go through an assessment, just from a place of warning from what I've seen in the industry, just make sure they're off purlins, right? Make sure they're on the roof, they make on the rafter structures and on the internal columns if there are some. They're the most critical, I should say, the greatest strength in a roof structure. Don't rely on your purlins to hold the weight of a 500-600 kilogram pallet. You will see that pallet go straight through, and you don't want that. No one wants that to happen. And the difference between types of purlins. So obviously the C and Z purlin. In my experience, the Z purlins are usually a lot better because they have the opportunity to lap, and they're most commonly lapped. And lapping means that when a purlin runs over the top of a rafter, they kind of overlap for a certain distance to ensure that they're tight. The two purlins are tied in together. Whereas with C sections, we find a lot of the times you can lap them with back to back, but it rarely happens. And we find that they're usually single span or continuous. And single span is probably the worst case. And again, going back to their thickness and their sizes, the size and thickness is dependent, and what's good is dependent on how often they're spaced and the spanning lengths. You might have a 300 millimeter deep purlin, but if it's spanned long distance, it still might not be sufficient. But another thing I should raise in this is that thickness is critical. Understanding the thickness of your purlin, the thickness isn't proportionate to its capacity. Going from 1 mil thick to 1.2 mil thick doesn't increase it by 20%. It can increase it by significantly more. So having an accurate thickness measurements on your purlins is a really important factor to us, because there is a huge difference between the capacities from thinner and thicker purlins. Guys, that is it from the presentation. I really hope that I really don't want to make it too long. I really want to just be a nice summary of our process, a bit understanding of why we do what we do, and hopefully be able to answer a few more of your questions, that you've already had or the ones that you're about to ask. I will just open up the questions. There is a few that are here. So I've got a question from Kenan. I don't know if you can see it, but it says, what would some of the examples of purlins and rafter spans that you would start asking questions about? From the way I read the question, and what I think you're asking is what is a certain level of concern. So what should be some examples on purlins, rafter spans there? So I would say if you've got a purlin that's spanning, greater than 6 meters or 6 meters plus, you're going to have some concerns there, right? A purlin, it has to be a pretty good sized purlin to allow for a 6 meter span. If you have a really small purlin and it's spanning 3 meters, that would be a problem. It's too hard to say exactly what the ratio is between what size is good or what span is bad, because it is dependent on the size of the member structure. But in general, if you have something that's 6 meters plus between rafters, then you got to know, hey, that's something critical. I need to make sure the engineer's checking this. I would say, obviously, being an engineer, I would say check everything. And I've seen some really crazy cases for quite small spanning stuff, but it's almost a must at that point. It's almost something you really need to kind of worry about and look into in more detail. I've got a question from Marcus as well. Is there a rough weight of panel that you would determine as acceptable on north only before needing to consider installing panels on the south side, roof and balance the load? Yeah, it's a really good question. So Marcus' question is about the deflection discussion we're having before, and is there a rough weight of panels that should be there? Look, if I can answer honestly, Marcus, it is very case by case. As a rule of thumb, if you're going to be loading, if 100% weight on north is going to be on that side, I would say as a percentage, you should be putting it as something like 70-30 at most, 70-30%, sorry, at most, in the sense that there should be 30% loading on the south side if you're putting 70% on the north side. Again, it is very case by case in the sense that it really is dependent on the strength of the capacity of the building and the portal frame strength as well. So I can't give a very straightforward answer. What I will say is that we have to do a separate assessment when we're doing this kind of stuff, and obviously the budget would increase for our assessment in that case. That looks at the portal frame's integrity as a shape, and we apply loads on that to see if the deflection is okay when overloading the north. And that would be the separate assessment to check what you're asking, exactly what that limit will be. It's too dependent on the materials, sorry, the structure itself for me to give you a actual kilogram value though. I hope that was sufficient. I've got a question from Andre. Do you have someone in New Zealand that can do site assessments if required? We do have a few. Well, I don't say we have a massive range. What I like to say is that our site inspections are nationwide in Australia. We work with a building inspection company that can perform all site inspections Australia-wide. Now, they do have some contacts in New Zealand as an organisation, and we have used them in the past. It's not as commonly used, obviously, because although we do a lot of work in New Zealand, a lot of the times it's when it's just strictly a desktop assessment. Due to the nature, I don't think they expect to have us there. So a lot of the work we do, we already have structured drawings for the works. But if there is a requirement, there's two ways we go about it. The first one is talk to our building inspectors and see if they have any connections. And the second one is we can engage a local engineer and give them the training required to actually perform the assessment for us. Most engineers are very familiar with the structures that we're assessing and the questions we have around the sizes and spacings and thickness and so on and so forth. So to answer your question, we can figure it out. If you need it done and it's a must, we can definitely figure it out. I got a question from Aman now as well. Is it common to assess the whole building instead of just the roof members? Would Gamcorp cover this as a scope? Look, it's definitely common. Is it common? I would say no, it doesn't happen often. Is it a requirement that we needed to do in the past? Yes, it is. But understand, Aman, when you're asking someone to assess the whole building going down to its foundation, everything like that, that's a significantly bigger scope than any roof assessment you've seen. And it's actually harder to do than to actually design the building in the first place. I'll make that statement. Because when you're designing a building, it hasn't been built, and you can take considerations of something that you're about to design. But when something has been built, you have to check every connection, every detail, everything to the 10th degree, because a lot of the times you don't have the knowledge of it prior to building, or you can't see things as it gets built. So can it be done? Absolutely. Is it within any of your company's budgets to actually do it? I would personally say probably no. It's a significant cost to do what you're asking, to do a full assessment. I hope that answers that, Aman. Michael is in an auditorium. Would gantries, pathways that web access to the building under the roof for sound and lightning people that are attached under the roof, so it cause a problem with deflection? Okay, it's a great question. A question from Michael was, in an auditorium, they have gantries, and they're effectively like pathways, by what he's saying, where people can walk for lighting and sound purposes. And will this affect deflection? Again, Michael, I'll raise the point that it depends on what was originally. If that building was designed as an auditorium, which I assume it would be, then I'm sure that the engineer who's taken that into consideration, the engineer who's designed that has definitely taken them gantries into consideration. The same way we would take into gantries when we're looking at warehouse designs and other things as well. In saying that, will it play a part in deflection? Absolutely, it absolutely would. If it's being hung off the roof structure, then we might look at that particular area, add additional loads in that area, and look at the dead load analysis component of our assessment and say we're going to increase it by this amount of percentage because there is a gantry there, or there is something there. So I don't want you to turn around and say, oh, damn it, the job I did last week is probably going to fail. That's not necessarily the case. I would probably say that it's already been designed for, and the additional loads would still be okay, but it is something you should definitely be getting checked. Hope that answers that, Michael. Going to Mark. Mark, how does the age of the building affect your calculations from additional loads on the roof, given that you have all the structural drawings and the inspection from the installers? Okay, that's a really good question, Mark. So when you say age of the building, I'm going to make the assumption that the building is still in sound condition, and that the building is not rusty and whatever it is, but it's just an old but reasonably stable. Like it looks like the structural integrity is still there of the building. So how does the age affect it? It does to a certain extent. In our calculations, we do have to take that stuff into account. But as long as it isn't showing heavy signs of rust or heavy signs of actual, long-term damage, then the structure of the steel has a certain age, and that would still have its structural integrity. Does it take a part in our consideration? It does. Does it hold a significant weight? I would say no, it doesn't. I wouldn't be assessing a building that's 30 years old and 40 years old differently. They both have a certain amount of strength. I'm not saying there's no difference. There is a difference, but it's not a significant enough for me to be able to say one's going to work and one's not if they were the exact same building but 10 years apart. So again, everything I say, guys, although I am a structural engineer, I'm not a principal engineer. So a lot of these things have to be taken with a grain of salt. But from my experience, from my understanding, it wouldn't make a significant difference on the actual capacity of the steel members themselves. Another question from Michael. I don't know if it's the same one. I hope that answers that, Mark. Sorry. I hope that kind of summarizes that. Michael, east-west 30 degrees gable roof in Brisbane, built in 1900s-ish, old, hardwood timber, Colorbond roofing, better to load both sides of the building rather than having everything on one side? Absolutely, Michael. Absolutely. The biggest problem, there's two big things you said there, right? The first one is 30 degrees gable. That's a huge tilt angle with a huge face. I can assure you that when it's a 30 degrees gable, you have a significant truss underneath that roof sheet, and that truss is solely dependent on its shape. You're loading it on one side. You're making that triangle look like a U. And when you have that kind of loads, there is significant problems. The biggest problem, another big problem I have in the industry, is that people think, residential, it's small. I don't really need to do structural reports. And I'm not going to try and convince you that you do need to do structural reports, because it is quite expensive for the output that you're actually getting. And also you wouldn't be able to compete with the other people that aren't doing it. But the truth is that even the small residential houses that are, high pitched roofs, there's huge structural problems there. And there's huge problems with, 30 degree build and smashing out the northern side. That truss is now a different structure altogether now. That's not what the engineer initially designed for. Again, Michael, don't want you to run back to, if it's the same Michael, but to both the gantry job and the gable roof job, but I hope the point's somewhat clear in regards to the concerns. I got a question from Ali as well. The first slide where you showed the failed roof on the school in that's not in Queensland. Sorry, that's not in Queensland. That's overseas. Was that failure due to the roof sheet structure being bad to start with and would have collapsed anyway, or because of panels additional windows? Okay, sorry, Ali, I will confirm for everyone. Kendar School is not in Australia. I believe it's in the Southeast Asia. The learnings from that, I'll go into it a bit I'll answer your question and then I'll go into that a bit. So to answer your question, Was it failed because of bad structure, or was it because of the additional panels? So the way it worked with that particular Ken Dust school is that it was an old installation method of solar panels, and our Australian standard is far greater than that. So I'm not going to make a statement around the installation method, but what had happened is that their flush installation had allowed too much of a gap between the panels and the roof sheet, which effectively worked like a blanket. If you have a blanket on a bed, and you were to put a massive gust of wind on one side, you would see the air travel from one side of the blanket to the other side of the blanket if it was a big enough gust. So same thing happened in this case. This school it's a safety zone, right? So a lot of the places, it's been there for a lot longer than the panels were there for 3-4 years, and you've gone through bigger storms before. But now with the addition of panels, this gust of wind that got underneath the solar panels, firstly dislodged panels, and then secondly, when it starts dislodging panels, actually ripped off the roof sheet as well. And then the biggest damage was actually when these panels were actually in motion, they would come down through different buildings at impact and then cause further damage. So it's a very critical situation. Now, going back to the main point of that, the reason I put Queensland on that slide is just to understand that different regions have different forces. In Australia, our region of somewhat critical is coastal north kind of region because of its like cyclone zone prone area and whatever it is, and just in general high gust wind speeds as well. So just want to clarify that Ken Dust school is not in Australia. Lastly, guys, I think that's everything. I think I've answered all your questions. I'll leave another space for a minute in case any other questions come up. One thing I will end on is, please, guys, as you see, it's quite a short presentation. I hope that you actually got a lot out of this. I hope that it was productive for you guys as well. I really encourage your sales team to get on Friday's presentation. And then next week, we're going to be talking about site inspections and roof sheets. If there's any other presentation, I really encourage you guys to come to is next Fridays in regards to roof sheets. We're going to go through why there are concerns. We went through a good summary there in today's slide, but in general, we're going to go through a bit more details about what failures we've seen and what the manufacturers like Clenergy and S5 are doing to try and overcome these issues. But guys, without taking any more of your time, I will end it on that note. Thank you so much for coming. I'm really impressed by the attendance. It looks like the industry is eager to learn some things. So I really look forward to the other prep webinars as well. And if there's anything else